The camera sees what the quantum knows. That's all. Very easy.
One
photon hides, one photon glows. The camera sees what the quantum knows.
Across the World Wide Web, on your mobile devices, on social media platforms, this is Jambo Radio! www.jamboradio.co.uk. We are multilingual. We are conversational in the languages you best understand. We are Jambo Radio! Jambo Radio, inspiring transformation.
This is the Science Show with Dr. Dada. It's just so nice, you cannot do without. This is the Science Show with Dr. Dada. It's just so nice, you cannot do without.
Well, hello, and welcome to the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. Now, tonight we're going to be asking a question that sounds impossible. Can a camera see light that it never detects? Yes, it sounds crazy. How can you see something when when you don't detect the light? I mean, what are you talking about? Well, our title today is The Camera That Sees the Invisible. And we're going to be talking about quantum imaging with undetected photons. It's a beautiful idea where one photon interacts with a sample, but its partner is what we actually detect, not the one that interacts with the sample. So what that means is that information from infrared light, which can be very expensive and difficult to measure, can be transferred into visible light that ordinary silicon cameras can capture. So my guest today is going to be Emma Pearce, whose published work includes practical quantum imaging with undetected photons, yes, and single frame quantum holography and quantum undetected optical projection tomography. Yes, all those wonderful sounding things. We're going to be breaking it down today, bringing it to a human level, and we're going to be making it fun and very clear, of course. So things like, what is a photon? What does undetected really mean? What does detecting mean, And why could this help things like imaging, materials, biology, and everyday technology? And of course, you can call us during the live broadcast. The number to call is 0141 530 2787. That is 0141 530 2787. And of course, this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting live from Glasgow. We would like to thank our supporters on this show, including the IOP, University of Glasgow, the PSRC, and of course, as you know, you can listen on DAB, and you can also listen and watch us live at jamboradio.co.uk. Episodes will also be uploaded to our YouTube channel, Jambo Radio Scotland, and also the dedicated YouTube channel for the show, which is T Science Show on all platforms. Great. So before we get into our interview and before we introduce our guest today properly, we'll just go over one of our science highlights for today. And this one is actually quite interesting and close to home. Is coming right out of the University of Glasgow. Now, when you've been sitting so long that standing up feels like your body has to reboot. That feeling. We cannot relate to that, especially if you have a job that requires sitting down for a long time. Now, a University of Glasgow-led study followed more than 91,000 UK biobank participants. And the researchers used wearable activity data and tracked health outcomes across roughly 12 years, so over a decade. And it was more than asking people, well, did you exercise or did you not exercise? This was really detailed. They looked at how long participants stayed completely inactive without getting up or moving around, and what they found was a little bit troubling. They found out that long unbroken periods of sitting or reclining were linked with a higher risk of dying from cancer. Each additional hour or prolonged inactivity was associated with about a 10% increase in cancer mortality risk. So every hour counts, 10%. That's wild, isn't it? I think that's really wow. That's really interesting. But here's the useful part. The pattern appeared less harmful when people regularly interrupted their sitting with simple movement. So this is not about going to the gym. Simple things like just, standing up, going to the kitchen, doing light housework, or standing during a telephone call, for example. And this is where it suddenly makes sense. Exercise is still important. I mean, you can't, then say, oh, wow, you don't need to go to the gym anymore then, right? That's not what we're saying here. But what we're talking about here is the pattern of your stillness. The period during which you have to be seated or be kind of still, the way you manage that is also very important. And of course, this study cannot prove, it's not like definitive proof that it's the prolonged sitting that directly caused these deaths. There's a lot of things that the study probably doesn't cover. For example, is this causation or is it just correlation? But at least it gives us a beautiful, simple daily rule. I think, set a reminder every 30 minutes, move briefly, and then sit down again. It's not so difficult to do, is it? So that's the first highlight for today. If you want to learn more about this, again, as I said, that came out from the University of Glasgow, and it's published in PLOS Medicine UK, and published this month, the month of July 2026. And in fact, it was reported in The Guardian, so you can find out more about that there, including the details of the publication. All right, so that brings us back to Emma. So we're going to get to know Emma Pearce, who is our guest in the studio today. So first of all, let me say a warm welcome to you, Emma. You're welcome to the Science Show. It's nice to see you and to have you here on the show. It's been a long time we've been trying to get you into the studio, but we're glad. I've
been looking forward to it since the day I started at Glasgow. It's
amazing.
The pinnacle of my career so far.
Fantastic. Great. So, this section is basically designed to kind of get to know you a little bit better as a person. And we'd like to do that on this show. So, let's start with this one. When did the interest in things like light, optics, or even quantum begin exactly, would you say?
Well, that depends who you ask. So my dad will absolutely take credit for my interest in quantum physics. But I'd forgotten about that until I told him that I wanted to do it at university.
I see.
So he's an electrical engineer by trade, but has always found physics really interesting and would watch a lot of documentaries and Jim Al-Khalili, this kind of stuff.
Oh,
and so we'd watch those together when I was really young. And then I forgot all about it because I was 4 and it didn't mean a lot to me, talking about entanglement and things like this.
Yep.
And I actually thought that I wanted to study medicine as I was going through sort of high school and thinking about applying to university. And it wasn't until just before I started applying that we started doing lectures on physics that actually were much more interesting than what we'd done in high school.
I see.
And it was at that point that I was like, I think I'm going to sack off this medicine thing and then maybe I just do pure physics. Like, this is what's really exciting to me at the moment. And when I said that to him, he was like, well, obviously you've always loved physics, you've always loved quantum. And that's when I found out that I've been prepped from a young age for this path.
Interesting. That's very, very interesting. I noticed you said something about first being interested in medicine. Can I ask a bit more about that? Because I had a similar experience. I actually did the entrance exam, to do medicine. But then by the time the results came, I changed my mind. I decided, okay, no, I'm not doing that. So what would you say gave you that interest in doing medicine, to start with?
Well, I think that it's something that people fall into by default, where if you're good at the sciences at school, it's an obvious path that people push you down. Yeah. Where people understand what medicine is about.
Yes.
So, I mean, I don't know how it was for you, but I certainly didn't have teachers at high school that were specialists in their subject. I didn't have a physicist teach me physics or a chemist teach me chemistry. Yeah. And so I think there's probably a bit of a lack of awareness of what it means to study a pure science in that case. Absolutely. Whereas medicine feels like a sort of well-trodden path that people understand where that leads to.
Yes, and it's easy. I mean, it's so relatable, right? Medicine, doctor, they know exactly what you're on about. So, okay, great, fantastic. So, How would you explain imaging then? Imaging with undetected photons to, let's say, a clever 12-year-old, would you say?
Well, I mean, this is something I've had a fair bit of practice in. We like to do a lot of outreach with what we do. And it's a really fun game trying to figure out how to pitch it at different levels. I think the first thing is making people realise that normally when you take a picture of something, it's because light has hit an object and that has reached a camera of some kind. And normally we do that with visible light. People typically want to take pictures of the things they can see. So we have all these fantastic cameras that capture the bit of light that we call visible. But there's all these other bits of the spectrum that we don't see with our eyes and that we don't have good cameras for. And there's all sorts of extra interesting information in those parts of the spectrum. And so this is a technique that brings in different bits of quantum physics to be able to get those bits of the spectrum talking to each other. I want the best of both worlds. I want the interesting information from the infrared, where I can do all sorts of things that I'm sure we'll talk about in a moment. Sure. But then using all of the really easily available, well-developed technology that we have in the visible.
Yeah, that's amazing. Well explained as well. You've had practice for sure, I can tell. So, now when people hear undetected photons, what would you say that they easily misunderstand first?
There are a number of things, and you get it from people at all levels. It's not just explained to 12-year-olds. There are plenty of people much more advanced in their careers that misunderstand this quite regularly. I think one thing that's important is that I can't just send my light off into the universe forever and never do anything with it. The devices that I make to be able to do this imaging with undetected photons, they're closed systems. I need the infrared light to come back to me in some capacity. I just don't send it off to a camera itself. And so a lot of people end up thinking that this leads to sort of a faster than light communication, because they imagine that I send off the infrared across the universe. You know, when people talk about entanglement, a lot of the time the cool thing is that you can send them to the other side of the universe and they still talk. But that's not what I'm interested in. I'm interested in the fact that it comes back and I can harness that information in a way that's totally allowed, doesn't break any laws of faster than light communication.
I see. Wow, that's interesting. Yeah, it's nice to make that sort of clarification, isn't it? Because when you say undetected, it's like, oh, it's undetected, it's gone.
Yeah.
You know, there's, you still need the information that it's there, right? The fact that it's undetected just means it doesn't interact with the setup or the sample that you want to measure. So you're not detecting it in that sense, you're not measuring it in that sense.
Exactly.
So yeah, so it's good to clarify that. Amazing. So now talking about why this approach is so useful, right? Because we know it is very useful, but how would you explain that? So why is infrared imaging so useful? And why can infrared cameras be difficult to get or complicated to use or maybe noisy, would you say?
All of the above. So the majority of the time, the reason we're interested in looking in the infrared is because you get really specific information about what stuff is made of if you look at how it absorbs infrared light. Amazing. So everything is made of molecules, and those molecules will vibrate and twist around at some particular energy. And the energy that does that matches the infrared part of the spectrum. So if you shine infrared light at a particular molecule, it'll absorb that in a very specific way that tells you exactly what it is on a molecular level. And so there's a region of the infrared that often gets called the fingerprint region, because it serves as a fingerprint of identifying what it's made of. So obviously that's useful for a really wide range of things. Yep. We use it to identify plastics. It's very interesting for diagnostic medicine. You can identify, based on the molecular composition, DNA in a cell compared to other proteins, and this ends up being a really specific biomarker for things like solid cancers. So yeah, the main thing is that it's a really specific source of information, and that's why it's so powerful, because you can apply that to pretty much anything, because everything has this signature. Yeah,
that sounds amazing. I think this is really what sharing, isn't it? Because, that sounds really, really important. Usually what I find is when somehow you can connect what you're doing with some of the challenges, the world's challenges, then it becomes really interesting, doesn't it? And yeah, it's amazing. And I know you got funding recently Would you like to tell us about that? What's that project going to be about? Is it related to this as well?
It is, yeah. So I mean, I've worked on imaging with undetected photons all the way through from my PhD until now, and I'm not intending on stopping apparently.
That's good.
So a lot of the work is very much focused on the applications of this and pushing to whatever wavelengths you need to be able to do these different diagnostic techniques for whatever application it is. I'm going in two directions. One is a bit more of a fundamental approach. I want to see what we can do to improve the resolution.
Yeah.
So microscopy has had all of these big revolutions from super resolution techniques.
Yeah.
They come in all different shapes and forms, and I kind of want to see what can I borrow and learn from classical microscopy and apply to these systems, so that then hopefully that can be used for things like the diagnostic medicine type of applications. So that's one side of it, sort of a bit more exploratory, a bit more fundamental science. And the other side is that I really want to make these systems look like microscopes. And I think, well, the hope is that means it gets into the hands of people who would then use it and they sort of know what to expect. I would much rather people used it because it was useful rather than because it's quantum. And so if I can put all of the quantum magic stuff into a black box that I hide inside of a microscope, and the person I give it to doesn't have to understand anything about it, they can just use it like the microscope they used to. I think that's the goal.
That's wonderful. It's nice. It's a really neat idea. That's what I like about it. It's very neat, and it's, you know, it works. It's practical. It's something that you can actually see how it goes into society and makes impact. It's beautiful. Fantastic. So what would you say was the first experiment or idea that made you think, okay, this is what I'm going to do. This is worth pursuing as a field, or maybe as a project, or, you know, whatever level?
That's a really interesting question. I think the first time I got into doing experiments at all, because the first couple of years of university I did not enjoy the experimental physics, but I'm not good enough at maths to do the theory either, and I was like, I don't know where I'm going to sit in this. And then it was in my third year, so I did my undergrad at University of Sheffield. And they do this really fantastic programme, I hope they still do it, I'm not certain, called an extended project. And there was a number of us that could do a quantum optics lab. And you rotated through 3 different experiments that were sort of some of the core early experiments used in quantum optics. So there's the Hungy-Mandel dip, there's a Hanbury-Brown twist. Nice. That was the first time I made a pair of photons, would have been in that lab. At the time I had no idea what that meant. But I think that sort of hands-on work on something that was also theoretically really interesting. It's probably the first time that we really made the connection between the interesting stuff you learn in the quantum lectures and what it actually means for people who do that in research. And I think that kind of project and getting that into undergrad life is really important for teaching people what it means to do research. Yes,
I'm really glad to hear that. You know, sometimes when you teach these courses, you're wondering, I hope it's useful. I hope it's something that has impact on their careers, ahead. And it's interesting. So hopefully they're listening.
Shout out to Luke Wilson.
Good. Great. So what we're going to do now is we're going to take a music break. And after the break, we're going to be asking Emma how a visible camera can reveal information from light that it never directly sees. And of course, as usual, you can call us. Again, the number to call is 0141 530 2787 rather. So 0141 530 2787 if you have any questions about photons, about cameras, or any quantum weirdness. Emma is going to answer your questions. So for our music break, we're going to listen to État Major by Extra Music, and we'll be right back. Wow, that was État Major by Extra Musica. Amazing music. The language is Lingala. It's a style of music called Seben. It's amazing. It's very, very organic. I love it. It's actually having a comeback now. This song is from the 1990s or early 2000s, but it's starting to have a comeback now, this style of music. And this is the Science Show with Dr Dada on Jambo Radio Scotland, broadcasting live from the city of Glasgow. Again, we'd like to take this opportunity to shout out to our sponsors, the Institute of Physics Scotland, the EPSRC, the University of Glasgow for the support. And again, you can call and speak to us on the show live through this number 0141 530 2787. That's 0141 530 2787. So let's get back into our discussion. We've been talking to Dr. Emma Pearce about seeing things that are invisible, which is quite interesting. And along similar lines, we have our second news highlight before we continue our interview with Emma. And this is about something very, very weird. Black holes. You've probably heard about black holes quite a lot if you've been following this show. And this highlight is about something to do with mergers of two black holes. You know how you can see something? You know that feeling when you can't see a train coming yet, but you can hear it coming? It's something similar that's happened with this discovery. So scientists are studying the darkest object in the universe by, you could say, listening to it without directly seeing it. So the researchers have analyzed a gravitational wave signal called GW250114, and they found a possible clue from extremely close to a newly formed black hole. Now, this signal came from two black holes colliding, and that collision shakes space itself, and it sends out ripples that we call gravitational waves. It's a bit like dropping stone in water. You know how you form ripples around. Yeah, it's something like that. And it's different from, waves traveling through a medium, or even electromagnetic waves traveling through space. This is the actual fabric of reality, fabric of space and time itself, vibrating, so to speak. So it's actually quite wild, isn't it? Now, a black hole has something called an event horizon, and that's the boundary beyond which even light cannot escape. Because as you know, black holes are so heavy that the gravity kind of bends space-time around them, but it sucks everything in. And even light, even though light is massless, light gets sucked in as well. So, things like ordinary telescopes, if you want to talk about detecting things that are invisible, right? If you want to kind of take a picture of a black hole, you can't, because no light escapes from it. So you can't see what happens there. But gravitational waves, because they're different from light or radio waves or electromagnetic waves, these distortions in space-time is something that you can actually measure. So it's a bit more like you're listening to the rumbles rather than actually seeing the train coming, so to speak. So these researchers think that part of the new data, GW250114, may actually contain a direct wave signature. This is what they called it. Direct wave signature from very near that horizon. In other words, they may be receiving information from a place that can never send us a photograph, so to speak. So before this becomes a confirmed new tool, more detections are needed. But this is what makes it special. The researchers claim that they've isolated an additional component inside the merger signal called a direct wave. They argue that this frequency and fading pattern carry information from very near the newly formed black hole's horizon, particularly its rotation and surface gravity. So it's a bit like, to use an analogy again, some of the weird analogies that we like to use. So the normal gravitational wave detection is a bit like two cars crashing, right? So when you hear the crash, if you analyze just the sound, you can maybe say something about the masses of the cars, the weights and the speeds at which they were going, right? Now, this direct wave analysis is a bit like someone saying inside the car crash recording, oh, I can isolate a faint sound produced right beside one of the wheels. I can tell you what kind of wheel is on the left, on the on the passenger side or on the driver's side, something like that. So this is the kind of detail that they're kind of teasing out of the data. So it's a bit like a new way to analyze the data, so to speak, a new way to listen to gravity, so to speak. So That's quite interesting. So black holes may be dark, but apparently they're not completely quiet in a kind of real sense of the word. So anyway, that's a very interesting highlight. It's again published in livescience.com, so you can find out more about that, including the work. So the reference is GW250114, and you can read more about that there. So going on with detecting things that you can't see, right? Infrared photons. So let's continue on our chat and our interview with Emma now. So first of all, let's go a little bit deeper. And would you like to explain to us, I know you mentioned it already, but would you like to explain a little bit more to us about this idea of photon pairs? Where do these photon pairs come from?
So the easiest way that people tend to make these pairs of photons is a process that gets called spontaneous parametric down conversion, which isn't super catchy, so we'd normally call it SPDC. And so you would take a laser and you put that into a special kind of crystal, and every time I put in one photon from that laser, one chunk of light, that can split into two new ones. And as long as I conserve energy and momentum in that, like with all good things, I can share the energy and momentum around with that however I like. So I don't have to send in one chunk of light and split it in half and have two identical ones. I can do it so that I give more energy to one of them than the other. And so this is how I make a pair of photons where one of them is visible and one of them is infrared, because I share the energy around differently between them. And this is sort of the trick to get those parts of the spectrum linked in some way.
Wonderful. Thank you very much. And so why does the mere possibility, so now let's go a little bit more into some of the quantum weirdness here. So you've got these two photons, they share something called entanglement. And so, when it comes to the nonlinear interference, what's the basic understanding there? What's going on with nonlinear interference, would you say?
So nonlinear interference, or interference that uses nonlinear effects like making these pairs of photons, works exactly the same way as interference that maybe people come across during high school, or you just mentioned about waves on a pond rippling. That's typically the first place that people hear about like these wave effects, and when those waves come together, we say that they interfere with each other. The peaks can add together and you get a big peak, or the peak can add it with the dip and then you cancel out completely. And so this is a wave phenomenon, whereas I spoke just now about photons being chunks of light, which is like a particle phenomenon. And the way that we use interference, this is something that gets used in all different types of science. You mentioned gravitational waves, and the longer you do science, the more you realise that pretty much everything is an interferometer at some point. And the thing that, I'm going to personify the light a little bit here, if you'll allow me to. The thing that makes a system decide whether it's going to behave like a particle or a wave is something to do with what you know about that system. And so this is a rule that I'm just going to state, and you shouldn't think too hard about why it is, because you'll get lost in the philosophy. But as a rule, if there are two ways to get to the same outcome and you cannot tell the difference between them, then those two pathways will interfere with each other. So that could be that you send light clockwise around a system, or you send anti-clockwise around the system. If it ends up at the same point and at the same time, you can't tell which way it went, and you'll get an interference effect. It'll behave like a wave. But as soon as you do something that tells you which way it went, so if one of them had to, pass through a stoplight, and so it got slowed down on the way and they didn't arrive at the same time, you could tell by timing it which one went which way. And so then it will behave like a particle. And this is just something that we accept and we observe every single time. It's a really well-known, well-proven rule that we almost take for granted and use to measure things all the time. I don't have to look inside the box to know which way it went. I can just look at what happens at the outcome. Do I see a wavy pattern, the bright and dark lines, or do I just see a flat spot where everything cancelled out? And so with nonlinear interference, this is exactly the same, but what I do is I make a pair of photons in one direction, and then I make a pair of photons in another direction. And if I overlap them very carefully, I can't tell where they came from. And so the trick that we then play is that I only ever have to detect the visible light to see the interference pattern that comes from this. The its partner photon becomes a little bit redundant. You always know it had to be there, so you don't have to look at it directly. And if I do something that makes the pairs different from each other, and this is the key thing, it always matters what happens to the pair. You can't really separate one from the other. It means that if one of the infrared one gets absorbed, then now my pairs look different to each other because one of them isn't a pair anymore. And so this is how, without actually looking at the infrared directly, you can tell whether something happened to it by just looking at this visible wavy pattern.
Wow, that's interesting and very well explained as well. Wonderful. It's bizarre, isn't it? The fact that, okay, knowing something affects how a photon behaves. The fact that you know something, how does you know that you know, right? That's weird, isn't it? But also, it's even more wild than that, because the fact that it's possible to know is enough. Even if no sort of conscious mind knows, as far as we know, right? The fact that it's possible to know, the fact that there's a possibility of knowing a photon's path, that changes its behavior. That blows my mind.
Yeah, absolutely, because it really is, absolutely anything in the universe that could distinguish that. It could be like, the smallest angle between them, the slightest turn in how the light twists, and any one of those things would ruin the interference effect that you see. So the fact that it's ever possible to, sort of erase all of that information from the universe to the point where we see an interference effect in any of these experiments is remarkable.
It is, absolutely. Wow, amazing. So, your 2024 work, it points toward single frame transmission and phase imaging. So what's that about? How would you explain that to us?
So this is actually the work that brought me to University of Glasgow in the first place. I was presenting about imaging with undetected photons at a meeting for the funding body that we're part of. And a couple of guys from the optics group at Glasgow reached out to me and were like, we think we can do this but better. And I was like, oh, okay, fine. And so we came up with this idea to do it together. And the nice thing that they did was realise the link between digital holography, which is a technique used a lot in microscopy, that is based on interference patterns and interferometers, and how that might apply to the sort of non-linear interferometer that I typically work with. And so up until that point, to be able to get an image, you had to take lots of different camera frames, and between each one there's a stage that you have to move very slightly, and then you take a load of images and then you reconstruct them. And we could do that fairly quickly, but you still need to do multiple acquisitions, and actually the stage that moves in this process is one of the most expensive bits of the kit that we use. So they said we can get rid of that, and I was like, okay, great, let's do it. And that's actually how I came to work with the University of Glasgow for the first time. And typically when people think about quantum imaging, it's quite slow. You think, you're looking at individual pairs of photons and you're timing usually their arrival. And that is quite a slow process. You typically have to do in a dark room. But if we want to be able to use this in clinics and in different monitoring plants, then that's not going to be useful. And so anything we could do to make this faster was going to be hugely useful in terms of deploying this eventually. And so that work has a little trick in it where instead of moving a stage backwards and forwards, all I do is I tilt one of the mirrors, and that introduces a change in the same way that moving the stage backwards and forwards does. Okay. And so I get all of that information now in every camera frame I take. I see. And so I'm going to make a claim here. I think that's the first time anyone had done this at video rate, where you're not just acquiring the data, but you're also interpreting it to get the transmission and the thickness information all out at video rates. And people have taken this on into their own work in other groups now, where people have done incredible frame rates with this technique.
That's beautiful. Thanks for sharing that. It's amazing. It really is. And so what would become possible then if these systems move from the laboratory into measurements toward real-time imaging in hospitals or wherever they may be? What would you say? So
the one with, I think, the most exciting impact is in the diagnostic medicine. So this is something that I was involved with during the PhD at Imperial College London, and the work continues there on that, where the motivation is looking at tissue biopsies. So if someone suspects they have cancer, they feel a lump, a doctor would take a slice of tissue from that lump and they'd put it onto a microscope slide. And normally you then inject that with a vegetable dye that makes it go different colours of purple.
Yeah.
And the way that you make a diagnosis on the severity of that cancer is how purple is the purple, which is a very subjective decision to make. And obviously this is done by experts who are very well trained.
Yes.
But that level of human judgment introduces an error that you'd really rather avoid. And oftentimes it leads to people being overtreated. If you're not certain between two different doctors looking at the same sample, the thing you have to do is err on the side of the caution. But that's obviously deeply unpleasant for whoever has to go through the treatment that can be quite aggressive. And it's also really expensive for the NHS. So if you were able to look at these samples instead based on their infrared absorption, I said before that you get these fingerprints of what stuff is made of, and you can identify the amount of DNA in the cell and use that as your measurement. So it suddenly becomes very, very objective. You get a number, and there's a way to map what that number means to what it means to the cancer. So the hope is that this would be sort of another tool that doctors can use to reinforce the decision that they make. You know, we're not suggesting that we're going to replace everything that doctors have ever known, but the hope is that this is something that then sits alongside all of the other tests that they do to help be certain on exactly the treatment that people need and make sure that's no more, no less.
I'm sold. That's good.
Give me your money.
Take it. It's great. That's good. Honestly, it's really, really nice. I really love those projects where you can see the real connection. You know me. I really love my fundamental physics and quantum physics, but also, you know, when you can connect it to something that affects lives, you know, improves people's lives, that's really good. That's really, really good. So now we've come to the next music break, and this time we're going to be listening to a song released this year entitled Jo Ijo, which in Yoruba means dance the dance, which means dance, right? Just means dance. And it's by Tana Musica and Jo Ijo. And we'll be right back.
Everybody now. Everybody say Jo. Nice, eh? Yeah, Jo to the Jo, my Jojo. Jo to the Jo, my Jojo. You say Jo to the Jo, my Jojo. Yeah, Jo, 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 Jo. And the beat that's in my Jo, 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 Jo. I say Jo to the Jo, my Jojo. Jo to the Jo, my Jo. Akwala, la, oh. Jo, 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 Jo. Let's go, solo. Let me see you say Jo. Jo. Say Jo. 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 Everybody say Jo. Jo. Yo. Jo. Jo. I say Jo. 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 Epa.
Well, that was Jo Ijo by Tana Musica and Jo Ijo. Well, Jo Ijo, it's a J-O-E, you know, the Jo Ijo in the name. But the song is Jo Ijo, which is just J-O, and it's a Yoruba word. Anyway, this is the Science Show with Dr. Dada here on Jambo Radio Scotland, broadcasting live from the city of Glasgow. And once again, we'd like to take this opportunity to shout out to our sponsors, the University of Glasgow, IOP Scotland, the EPSRC, IAA, and everyone else tuning in and who've been supporting the show for all this time. We really appreciate your support and your tuning in and all your engagement on social media as well. It doesn't go unnoticed. And again, the number to call if you'd like to chip in is 0141 530 2787. That's 0141 530 2787. We're there live on DAB, and you can also listen or watch us live at our website, jamboradio.co.uk. Episodes will also be uploaded onto the Jambo Radio Scotland YouTube channel, as well as the dedicated YouTube channel for the show, which is T Science Show. So now we've come to this section where we're going to be talking about applications. And the question for the week is this: if a camera produces an image using photons that never interacted with the camera, should we call that seeing or sensing or something even stranger? What do you think? Well, if you have an answer for us or any ideas, please again call us and let us know your thoughts. 0141 530 2787. And we're going to get an expert answer to that, of course, at the end of this section. But that's food for thought for everyone at home just now. Anyway, let's carry on with our chat, Emma. So this part, we're going to be connecting your work to useful, and there's a lot of connections, but just a little bit more into, things like imaging. We've already talked about that a little bit. Chemistry, environmental monitoring, potentially, biological samples, and future experiments that may become cheaper, smaller, or more portable as a result of this technique. So let's start with this. Where would you say this could be more useful? Is it more materials? Is it medicine? Or environmental sensing, semiconductors, or something else? What do you think?
Well, I suppose the thing that you gain in each of those might be quite different. So for the diagnostic medicine, the barrier is often the noise in the camera if you were to do this with an infrared camera. Mm-hmm. So the light that you're trying to detect in that case is the same as the thermal background in the room. And so you very quickly get swamped out by the fact that your infrared camera also sees the fact that the room is glowing as well as your tiny little cells in your sample. Yes. So you'd get an advantage in, for example, noise in that case. Whereas for things like the environmental monitoring, there's some work that came out recently from the time that I worked in Berlin at Humboldt University there, where we make these really fantastic compact modules that are able to do spectroscopy in the infrared for identifying plastics. And the goal of that project in the long run is to be able to identify microplastics in wastewater and to be able to do that sort of on site. And so in that case, the advantage is because you can make it very small and very compact. Again, we don't have to be in these big dark rooms like a lot of quantum is imagined to be. Yeah. And so the way you typically do that now is these things called Fourier transform infrared spectrometers that can be really big and bulky and expensive by the time you get, a laser that works in the infrared and a camera that works in the infrared. Yes. And we take all of that away and put it in these tiny little boxes. And so in that case, the advantage comes in sort of footprint and cost. And so for all of these different applications, there are different niches you're trying to fill. Yes. Which is a sort of generally something that quantum imaging does. You can tailor it to the different application.
Wow. That's amazing. The spectroscopy is becoming more and more interesting by the day, isn't it? I was visiting a lab the other day at St. Andrews, and they were showing some spectroscopy where they were trying to detect counterfeit drinks, like whiskey and things like that. And I thought that was wow, this is really, really, really interesting. But now you're taking that into the quantum realm, so to speak, isn't it?
Yeah, maybe I should start looking at drinks. That sounds like a fun project.
Yeah, it would be. And you talked about plastics as well. Yeah, plastic sensing. That's really interesting because microplastics are in the news a lot these days. So anything that could help with something like that is going to be hot.
Exactly, yeah. That's the hope.
Amazing. So, okay, what about 3D imaging? So quantum undetected optical projection tomography. Sounds like a mouthful.
It is. What's it about? It's a lot of words. Yeah. So this is some work from Imperial College London again, from while we were there. And in this case, what we're doing is the sample itself rotates. And without really changing anything about the system that we typically build, just by rotating the object and being careful about how you put that data back together, you can get the full 3D profile. And so this is one approach to being able to do 3D imaging. There are a number of other ones as well that I'll maybe get into some of the stuff I'm hoping to do in the future. with these sort of resolution enhancement techniques. Some of them also lend themselves to being able to do sectioned imaging, where you take different slices and then you add them together.
I see.
So yeah, this is one route to be able to do 3D imaging. So when we did that, we kind of did it just because it's a bit of fun, and we realised that there's this link between how you can process the data in the way to make this 3D shape. We're not sure what we want to do with that yet, but if anyone has any ideas, do let me know.
Good. Yes, please do let us know. And if you want to, call in and tell us right now, that's also great. 0141 530 2787 is the number to call. And you can ask Emma your best question about photons, about cameras, or infrared light, or any weird rules, weird quantum things, So, now, there's this aspect of sensing that I find very interesting. So this idea that you could measure samples that are too sensitive to strong light. Could your technique help with that?
Yeah, so it lends itself very well to that. So typically we're working in a very low light regime, but that's not a problem because we're using these visible cameras that are super efficient. Yeah. So even though, before I said that I put a laser into one of these crystals and I make my pairs of photons, the chance that a particular photon entering that crystal splits into two is like 10 to the minus 3. So it's decimal point and then 12 zeros, and then that's a really, really small chance. Yeah. So I'm not making a load of light, but I can still detect it because it's a super good camera. One of the sort of more out there applications for this, where you really care about the fact that it's not a lot of light, is in art heritage conservation.
Yep.
So one of the other cool things about infrared light is that so longer wavelengths can penetrate into materials further than shorter wavelengths. Yeah. And so we've done a little bit of that for things like ceramics inspection. And you can also apply this to identifying different paint layers in artworks. And this is a real use case where having a low light level and being able to leave it running for a long time and build up a really nice clean image will be very useful.
Wow, that's wonderful. It seems it's an endless list of applications.
It does feel that way. It'd be great to have time to do them all.
Yeah, the more you talk about it, you're like, oh, you can do that. Yeah, you can do that. That's wonderful. That's how to choose a subject that kind of serves you your entire career, isn't it? It's really, really nice. Wonderful. Okay, so now let's open this up a little bit. So what's the most sci-fi sounding part of your work, would you say, that's actually real physics, but it sounds, what would you say?
I think it's the fact that I use crystals.
Ooh.
That very quickly gets people from...
How do you mean crystals? What kind of crystals?
Yeah, exactly, right? People always ask, like, what is it? And they're hoping that it's something like, rose quartz that you can get in the crystal shop. And I'm like, no, it's, periodically pulled lithium niobate, It's, so I think the fact that I genuinely use crystals to convert frequencies, I get the high energies and the low energies, and I can convert one into the other. That sounds very, very sci-fi, very spoopy.
Yes,
but
absolutely.
If you get the right kind of crystal, then you can do this.
Yes, indeed, wonderful. Okay, one more question. If funding wasn't a problem, what would you build next? Like, if you had all the money in the world to do whatever you wanted.
Yeah, if I had access to all of the materials and all of the time, then I think the step towards building one of these systems that's useful, that could go straight into a lab, is almost purely engineering at this point. Yeah. I think we understand the physics of how it works, and there's still bits to be done on that. There's other knobs to turn. But I think if I had absolute free rein, it would just be get all of the components and get a team of people to do all of the different aspects of it that are specialists in that, and get it to something that is useful out of the lab. Let's not be in the lab anymore. Let's get out.
Yes. Oh, wow. Yeah, we could go on and on, but it's time to say good night. We've come to the end, the time to round up on the show. It's been amazing having Emma with us, Emma Pearce. And this could have been like a 3-hour show, right? Very easily. But yeah, we do have to go now. But before we go, we're going to get Emma to rap for us. How would that be? That would be amazing. Don't worry, Emma. Yeah, no pressure. But DJ, could you give us a beat, please?
No way.
Could you give us the beat? Let's See if we can round up with that. I'll just get you to repeat after me, okay? Yeah, is that okay?
Yeah, go for it.
Okay. It's a very simple beat. So what you're going to repeat is 1 photon hides, 1 photon glows. The camera sees what the quantum knows. That's all. Very easy.
Are you going to do it with me?
1 photon hides, 1 photon glows. The camera sees what the quantum knows. Yeah? So I'll repeat. I'll say one line.
Let's do it together.
Yeah. I'll say one line and then you repeat that line. Okay. Are you ready? 3, 2, 1, go.
1 photon hides.
So, okay, I'll start. 1 photon hides.
1 photon glows.
1 photon hides.
1 photon glows.
The camera sees.
What the quantum knows.
The camera sees.
What the quantum knows.
1 photon hides.
1 photon glows.
1 photon hides.
1 photon glows.
The camera sees.
What the quantum knows.
The camera sees.
What the quantum knows.
Yeah, it's as simple as that. Great, amazing. Thank you very much, Emma. See, raps are so easy to do, right? You just put this. Amazing. Thank you very much, Mr. Producer. So you just, put the words down and just speak them to the beat, and that's it, right? Anyway, well, that brings us to the end of our episode today. Thank you very much for tuning in. This has been the Science Show with Dr. Dada. Today featuring Dr. Emma Pearce, a research fellow at the University of Glasgow. And until next time, stay curious. We're going to leave you with this track. Again, another Congolese track. It's entitled Afro Mbokalization. And it's by Afara Tena. And until next time, stay curious.